In this highlight video, we will apply what we learned about the substitution reactions of alkyl halides to the substitution reactions of alcohols. After watching this video, you will be able to contrast the different approaches to carrying out substitution reactions of alcohols. Now this video is a little longer than usual, so either stick with it or come back more than once. For a substitution reaction to take place on an alcohol, that alcohol will have to behave as a leaving group. So the first question is, will OH behave like a halogen or behave like a normal leaving group? Let's compare two different reactions. We have a generic nucleophile, but for alkyl halides, we know that this nucleophile will react with an alkyl halide and do a substitution reaction. I've drawn this out as a SN2 substitution to give us our nucleophile plus our leaving group. So the question is, will this same reaction take place for an alcohol? So we have our alcohol here. Will the nucleophile go like this to give us OH minus as a leaving group? What do you think? In fact, this reaction doesn't work. Why doesn't it work? Why do you think it wouldn't work? Well, an important part is that hydroxide is a strong base which makes it a poor leaving group. So OH minus is a poor leaving group, whereas bromide, we know, is a good leaving group. So to overcome this, what if we just use a stronger nucleophile? Alright, so what if we use, let's just pick an example, we'll use a very strong nucleophile like this acetylide anion. So will this be strong enough to push the hydroxide off? In fact, if we do this, it is strong enough to react, but it won't do the substitution because this acetylide is such a strong base, all it will do is an acid-base reaction. So we have two problems. One, if we have a nucleophile that's too weak, it isn't strong enough to displace the poor leaving group hydroxide. If the nucleophile is too strong, it becomes too basic and it just does acid-base chemistry. So we have to find a way around this. There are three strategies that we're going to take a look at, and all of them involve making OH into a better leaving group. The first one we'll look at is simply protonation. So if we add a proton to OH, we end up with water. Water is much less basic, and so water can be a much better leaving group. Another strategy will be to use several phosphorus and sulfur reagents, and each of those will allow OH to be made into a better leaving group. And the last one is to include the formation of what are called alkyl tosylates. So we'll go through these one at a time. If we treat an alcohol with a strong acid like hydrobromic acid, the first step will be that the non-bonding pairs on the oxygen will react with a proton and we will protonate that oxygen. If we do that, it converts the OH into a water molecule. Okay, that water molecule is still attached to the molecule, but now it becomes a good leaving group. So in this reaction, because we have a tertiary center here, this is going to proceed by an SN1 mechanism. The water can come off like this to form a tertiary carbocation. Once that carbocation forms, it can react with bromide to form the substitution product. So this reaction follows what we learned for alkyl halides. It takes an extra step to form the good leaving group. So this is an SN1 mechanism. All right, let's look at the second example. Now we're using HI. Again, we have a strong acid, protonates the alcohol, gets us to here, and for secondary with a weak nucleophile, we're again going to go by an SN1 mechanism. So this will form a carbocation like this, and then iodide can react either from the top or from the bottom to give two possible stereoisomers. Okay, this methyl group is remote from the site of reaction, so it stays the same. If iodide comes from the top, we'll get the cis product. If the iodide reacts from the bottom, we'll get the trans product. Now, likely, these will not be formed in identical amounts, and so this reaction very well might be stereoselective. Now let's look at the last reaction. It's going to start off the same. Hydrochloric acid can protonate that alcohol. Again, to form a good leaving group. But what's going to happen after this? Is this going to follow an SN1 mechanism as well? Well, that's unlikely because this is primary, and because primary positions do not form carbocations, this reaction is going to proceed by an SN2 substitution. So the chloride will come in from the backside, displace water, and directly form our product. All right, so what we see is that by using these conjugate acids of nucleophiles, we can convert OH to a water, and then we can do either SN1 or SN2 reactions. Let's look at a couple more examples. So let's predict what we would see for the product of this first reaction. All right, we have a secondary alkyl halide. If we protonate it, form a good leaving group, likely go through an SN1 type of mechanism. And from everything we've seen, we should just get a substitution that will look like this. Bromide will be on the top, and the bottom, so we will form a pair of enantiomers, but this is what we would predict, right? Well, it turns out that this at least is not the only product. This is not the main product. All right, and the main product looks like this. Okay, so this is the major product. So how would that form? Okay, a good thing to do is to look at the reactant and the product, and let's see what happens. So notice in the reactant, we have all three methyl groups here on this same carbon, and one over here. And in the product, we have two each on the two different carbons. So somehow, one of the methyl groups moved to a new position. All right, so the way we can figure this out is by going forward from the reactant and backwards from the product. Okay, so what we would expect from the reactant, right, is we start with HBr. Let's just start up there. We start with HBr, and it protonates the OH, just like we've been doing on all of these other products. We make a good leaving group. The next thing that we've seen every time is then that leaving group comes off. And we make this secondary carbocation. Now somehow we have to move a methyl group, but before we do that, let's start at our product and move backwards. So wherever that bromide is, that means that the penultimate intermediate has to have a carbocation at that position. So we need to have a carbocation here where this bromide could react with that to get to our product. So the question is, how do we get from this secondary carbocation to the tertiary carbocation? All right, and why would we? So the why part maybe is not so difficult to understand, is going from a secondary carbocation to a tertiary carbocation is going from less stable to more stable. Okay, so we're going downhill in energy. We're going to the more stable intermediate. So what has to happen? So it looks like one of these methyl groups has to move over. And that's exactly what happens, is the electrons in this carbon-carbon bond can essentially jump over to the next carbon. And this is referred to as a 1,2 methyl shift. All right, 1,2, because those two positions are adjacent to one another, not because they're numbered 1 and 2 in any kind of naming. So the methyl group moves, taking the electrons with it, forms a new bond, leaving the plus charge behind. We go to the more stable carbocation, and then that reacts with the halide. Tricky, huh? All right, so let's look at the next example. Okay, in this case, let's see if we can predict whether something like that would happen. We're going to protonate on the alcohol. Right? We're just doing the same thing over and over here, again here. We form our water molecule, the good leaving group. It comes off. Forms this secondary carbocation. Now, is there a way that we could do some type of 1,2 shift or a carbocation rearrangement that would give us a more stable carbocation? Well, what we see is that we have a more highly substituted center just next to it. And it has a methyl group and an H. And in this case, if the H can move over, that is going to give us an extra, here let's draw in one H here already. That's going to give us two H's here now and a plus at the tertiary position. All right, this is a 1, 2, and we're jumping the hydrogen, but the hydrogen is moving with the electron. So we're moving actually an H minus. So this is a 1, 2 hydride shift. All right, once that takes place, we're at the tertiary carbocation. That's as stable as it can get. And iodide, the nucleophile, can react with that to form our product, which now has the iodide at the tertiary position. The second strategy was to use sulfur or phosphorus reagents. The first reagent is called thionyl chloride. Its structure is shown right here. And this reagent can help convert the OH to a chloride. All right, so the way that this works is the OH reacts with the sulfur and displaces one of the chlorines. This remote site stays the same because it's not being changed at all. Sulfur, oxygen, and chlorine, and a plus here. All right, and we kicked off chloride. So in the next step, pyridine, right, this is pyridine here, is simply going to act as a base and remove this proton. So I'm just going to neutralize that functional group. Like this. And now, in one cool step, chloride is going to come in here and displace this whole leaving group. So it's going to come in from the top, the backside. This carbon-oxygen bond is going to go over here to make an oxygen-sulfur pi bond, and chloride is going to leave. So what kind of a reaction does that look like? All right, so this is really an SN2 step because the chloride is displacing that whole other group. And so because it's SN2, we should get inversion of configuration. And so the chloride is up like this, plus we've given off sulfur dioxide, which is gas, which just bubbles out of the reaction. And we've given off hydrochloric acid. All right, so this has a net inversion. All right, let's look at the next one. This uses phosphorus tribromide. Oxygen reacts with the phosphorus, displacing one of the bromides. Oops. Like this, and a plus. And now here, just in one more step, the bromide that was kicked off again, just does an SN2 substitution. To give us our product. Like this. Okay, and this step right here is SN2. We would get inversion of configuration, but of course, because that's on a primary alcohol, we can't see any inversion taking place. There's no stereochemistry. The final way to make an alcohol into a good leaving group is to make an alkyl tosylate. So the way that this works, we use this reagent here, which is called toluene sulfonyl chloride. And what happens is that the alcohol displaces the chlorine to form an intermediate. It looks like this. And if we just remove that proton with pyridine, we generate our alkyl tosylate. So why did we go through all of this? What is this big group that we've just added? So we can understand this if we realize that this entire piece right here functions as the leaving group. Okay, so the leaving group equals this. And this behaves essentially like it was a bromide. Alright, so why is this a good leaving group? Because it is the conjugate base of a strong acid. Alright, and it would be, the acid would be like this. Alright, and this is called toluene sulfonic acid. It's very similar to sulfuric acid. All right, sulfuric acid is a very strong acid, so is toluene sulfonic acid, or sometimes it's called just like this, tosic acid. Toluene sulfonyl chloride up here is sometimes just referred to as tosyl chloride or just TSCl. Okay, just some abbreviations. Let's do some final examples. So here we have a toluene sulfonate. There's our tosylate. We're using a strong nucleophile. This is primary, so what type of a reaction should take place? This is going to be an SN2 substitution. We get this methoxy group plus our tosylate anion. All right, what about the next one? Secondary tosylate. We use cyanide. This is good, but it's not a strong base. Okay, so this is, even though it's secondary, this is pretty good at doing substitution. So we get this, it's called a nitrile, and our leaving group. All right, let's compare the last two. This combines a few things that we've been doing here. So if we use phosphorus tribromide, that's going to convert, let's do this stepwise, that's going to convert the OH to a bromine, right? And so what's the stereochemistry going to be? All right, so the first step, remember, is an SN2 step, so we get an inversion of configuration, like this. And then our second step, we use this sulfide in DMF, so it's good also at SN2. And so it's going to do another inversion, and we get this thiol coming forward. So it's like a double inversion. What's going on here? All right, let's look at the next one. Okay, if we do step 1, we form the alkyl tosylate. All right, and this doesn't affect the carbon-oxygen bond. And so then in the second step, we use the sulfide again. It does an SN2 substitution. And we end up with the thiol facing back. All right, so what's the relationship between these two? Okay, these are enantiomers. And look at this, by varying the steps, we're able to make one enantiomer or the other enantiomer. We can control the stereochemistry.